Hi, good morning, everybody. This is Mike Weaver speaking. I do apologise for the late start, but we've had a lot of problems with internet access and I've had to now do it from home. So if you could just bear with me, we're just on the way now and hopefully everything will work okay. So I'm Mike Weaver, Associate Director for Sigma-HSE, and I've had somewhere around 30 years experience working with flammability of gas, vapors, powders and dusts. And I sit on committees dealing with the fire and explosion standards in Europe. So today we're going to be talking about developing a basis of safety for powders and dusts. A little bit about Sigma-HSE. We're a group of companies. Sorry, I'm having a little bit of a problem here. If you can just bear with me just one moment. Right, okay, we're okay now. Sigma-HSE group of companies with headquarters in the UK, and we provide technical services in health, safety and environment to industry. The company consists of Sigma-HSE UK, Sigma-HSE India, and we have now an operation in the USA in Boston. Our areas of expertise are basically consultancy, testing and training. We're doing the training at the moment for you, but we have consultants that go out on site to do what we're talking about today, defining a basis of safety for you. And in order to do that, we provide the test data in our laboratory in the UK, and we also have another test laboratory in India looking after the Asian and Far East markets. We have highly qualified engineers, scientists and chemists, experienced professionals. As I said before, some of us sit on standards committees. We work with global industry. Personally, I've worked just about everywhere in the world, and we deal with people from the pharma, food, chemicals, utilities, personal health care, etc. Our resources: dust, gas, vapor and fire explosion testing, electrostatics. We have a chemical reaction hazard screening laboratory, and we work under ISO EN 17025 quality accreditation. Our consultancy team can provide a whole range of technical expertise, including looking at industrial fire and explosion hazards, electrostatic hazards, PHAs, QRA hazards, HAZOPs, etc. Also, we can help you with functional safety, such as layer protection analysis. And we also do training workshops either as a public unit, webinars, or we come to your site to give the training specifically for yourself. So let's start off now with what you've all come here for, which is the basis of safety. As you can see by the photograph, the company that looked at this obviously didn't have a basis of safety, and this is what we're trying to avoid. So what is a basis of safety? It's a combination of measures relied upon to ensure safety. So it's not just one thing, it's a combination of things. It highlights the aspects of design and operation which are safety critical. So it's not looking at design or process, it's looking at the safety critical functions. And to do that, we have to take into consideration what type of equipment you're using. Are you using silos, blenders, reactors? What type of process are you doing? Are you producing powders, gases, liquids? Are they flammable or not? The area where you're working, is it a hazardous area? It will be if you're dealing with flammable materials. And we have to look at what type of area it is. Is it a zone 0, zone 1, or zone 2, which are designated in the EU? Do you provide work instruction? In other words, do you have SOPs, etc., for your workers so they thoroughly understand what the process is about? So in order to build our basis of safety, it is necessary to have the following information available. You must have information on the equipment specifications. How fast does the machinery go? What sort of temperature does it reach? What is it made of? Operating procedures, as I said before, these are very important to ensure that staff understand what they're doing with the process. Hazardous area classification. Is it a very high risk area, such as a zone 0 or zone 20, or is it less dangerous, a zone 2 or 22? What sort of maintenance procedures do you have in place? Do you wait for something to go bang, or do you have preventative maintenance in place to ensure the system works to a high level at all times? What type of materials are being handled? You'll probably have materials which you regard as not being particularly dangerous. And you may have other materials which you look at and say, these are very toxic, for instance. But some of these materials that are not particularly dangerous from the point of human health may be dangerous from fire explosions, such as sugar, flour, etc., food materials. Flammability data, such as minimum ignition energy, layer ignition temperature, minimum ignition temperature, KST, Pmax, etc., may be required in order for you to build a basis of safety. It's no good just saying to somebody, we're using inerting as our system if you don't know what the LOC of your product is. So how do you know that your inerting system is capable of keeping the process safe? I've put a note here at the end. It says, with a world shortage of materials, many companies are now turning to new suppliers. Be aware, this could mean that some of the material properties may change. They may be finer, may have different impurities in them, etc. And therefore it's advisable to retest these products to make sure they fulfill the same criteria as what you've set before. So, first thing is equipment. If you look at the equipment, you have to consider what type of ignition source can it provide: mechanical, electrical, electrostatic, etc. So the equipment that you're looking at must be suitable for use for the product you're working with. So does it fit into your zoned area okay? Or is it a piece of equipment which is not EX rated, for instance? So having a knowledge of your equipment is very important. Procedures, operational and mechanical. You need to know how to operate your process, and the people pushing the buttons and pulling the levers have to know why they're doing it and at what time that they actually do some of these things. They must know something about the materials themselves. So you have to let them know if a material is particularly toxic or hazardous from the point of view of fire and explosion, and what you're doing about it as well to ensure their safety. Deviations are something we come up about quite often. You may deviate from a normal operating process because you say to yourself, well, we're doing a short run, so we want it done today. We're going to increase the pressure, or we're going to increase the rate of fill, or we're going to increase the temperature. If you're going to do these things, then you have to look at it before you do it. In other words, to make sure that your basis of safety is still effective. Human factors. Human factors are sometimes a big problem. Humans can do very good things. They can smell burning. They can hear a machine's not going right. And they can identify this to people and say, we need to shut the process down. before harm is caused. On the other hand, they can do the most stupid things you could ever believe in your life. So looking at human factors, you have to consider what you've got in place to mitigate the effects of the human being in the system. Material properties. Not just the flammability of the materials need to be considered. Are they corrosive? Are they toxic, for instance? If they're toxic, and I've come up against this on several occasions, people have put explosion vent panels in with a toxic material, and they could fire it straight across the public car park outside the building. So you need to know other properties, not just the flammability properties, before you decide to choose an effective basis of safety. Risk level and tolerance are another thing you may need to look at. If your factory is located in the middle of a city or town, and people are going by it every day, then you may say to yourself, an explosion vent panel going off all the time is not something that they want to hear. And before long, you'll have the local authorities on you wondering what's happening. Whereas if you're in the middle of a greenfield site, far away from people, it doesn't really matter whether you have an explosion or not out there from the vent panels going off. If the vent panels go off, there's no one around to hear it except for your workers. There's many more other things to take into consideration when you're looking at this. So please just don't think about these ones that I've talked to you about. Look at other ones that may be around that could have an influence on your defined basis of safety. Now we're looking at fires and explosions. And looking at this, there are three types of basis of safety to look at these risks. We could look at explosion prevention. We could achieve this by avoiding flammable atmospheres, either by not using flammable materials, using them outside their flammable range, or introducing inert gas such as nitrogen to make sure the atmosphere is non-flammable. We could look at avoidance of ignition sources. To do this, it's very difficult. You have to take into consideration absolutely every type of ignition source you can think of that's there. And you have to be honest with yourself when you do this. Don't try to pretend that you can do something if you haven't got the data to prove it. Explosion protection. This is quite a common way of dealing with things. Put in an explosion vent, for instance. But as I said before, this may reduce damage to plant and employees from the explosion, but you also may blast out toxic materials over your employees' car park. So how do we get a dust explosion anyway? We don't hear about them that much, even though we know there's quite a few go on, and the companies don't want anybody to know about it. Therefore, they're kept quiet. It's only the very big ones you tend to hear about. But in order to do this, to get a dust explosion, the dust must be flammable, combustible, and airborne to form a dust cloud. So these are the main factors that you need to look at. It must be flammable or combustible, and it must be airborne in order to form a dust cloud. Concentration must be within explosible limits. Now, when we talk about gases and vapors, we talk about the LEL or LFL, the lower explosion limit, or the lower flammable limit. And we also talk about the upper explosion limit and the upper flammable limit. Now, we normally believe that within these levels, the gas or vapor will be flammable. Outside, it will not. When you look at dusts, that we have a lower limit, the minimum explosive concentration, but we never use the upper limit. That is because, unlike gases and vapors, dusts settle. And as the dust continues to settle, so it goes into the flammable range. Therefore, it's very difficult to use this value. So we only work on the MEC, minimum explosive concentration. And if we keep below that, then there won't be a risk of a dust cloud explosion. Particle size distribution should be capable of propagating flame. Normally, anything less than 500 micron will fulfill this of propagating a flame. Now, the smaller the particle goes, then the more likely the propagation will be more rapid, be more violent, and therefore the material will become more sensitive to ignition and create a much bigger explosion. So you need to know the particle size of your product to have an idea about what you're looking at when you get it tested. The atmosphere that you're working in on the process, or the oxygen in it, needs to support combustion. In other words, you need to be above the limiting oxygen concentration. If you're below this, then you won't get a combustion because you have no flammable atmosphere. If you're using inerting, please don't think by making it 5% that this is going to work and you don't need to know anything about your product. I've been to companies where I've argued about this, and without them measuring the actual oxygen level within the system. And later on, we found out that there's been a leak in the system. It's actually been a lot higher in oxygen level in the system than what they believed. If they'd have had the LOC, they would have known what sort of leeway they've got with it. We'll talk about this later. You must have sufficient energetic ignition source. So if you've got a material that has an MIE of 250 millijoules, and you have an ignition source, a static ignition source present, but it only can produce 50 millijoules, then you haven't got a problem. So you have to have a sufficiently energetic ignition source to get the explosion. So if we look at the fire triangle on the right, you'll see we have the fuel. This must be flammable, combustible, and airborne. We have an oxidant, that's the air, and we have an ignition source of a sufficient energy. But how do we get an explosion? This is the fire triangle. Well, we have a pentagon. And now we need to mix the fuel in the air. So if it's airborne, this is exactly what you get. You get the fuel with the air mixed in with the material. And on top of that, we need to confine it. When it's confined, then you will get the explosion. Without the confinement, you would just get a fireball. So we put those things together, and we stand the possibility of having an explosion. So I talked about properties, we talked about toxic, we talked about corrosives, etc. But we also need to look at flammability. Why is this important? Well, unless we know what the material does, how are we going to build our basis of safety? So you need a good understanding of the explosive properties of the material. You need to know how sensitive they are to ignition. You need to know how powerful the explosion is if you're using vents. It helps you determine whether you can stay outside the flammable limits, working below the MEC. And another fact now is last year, in 2021, it was a legal requirement on European safety data sheets to put data about flammability and potential explosion properties. Testing can be split in 3 sections, so you don't need everything. You need it to prove your basis of safety. So we talked about explosion prevention, avoidance of ignition sources, how sensitive a material is, and explosion protection, how powerful the explosion is. The change in the EU safety data sheet is Annex 2 of REACH, and that has been amended concerning the compilation of safety data sheets as from the 1st of January 2021. So, as from then, it is now a legal requirement to include data for flammability. This could be MIE, LIT, MIT, PMAX, KST. The lower and upper explosion limits. So as said, for powders and dusts, we just need the MEC. And then the old ones, which are always on there, for gases and vapors, flash point auto ignition temperature. Now, dusts and powders have their own set of tests and values that you need to look at, different to gases and vapors in many cases. The most common ones that we would test for is minimum ignition energy. This looks at the risk from electrostatic spark discharges and mechanical spark discharges. The minimum ignition temperature. This considers hot surfaces, electric motors, for instance, grinding sparks, that type of thing. Layer ignition temperature considers, again, hot surfaces. So again, you may have dust settling on things like electric motors. You need to have this data to make sure that the rating of the electrical equipment is safe. And then you've got maximum pressure, PMAX, KST, ST class. These ensure explosion protection is safe and usable. The minimum explosive concentration considers the flammable range, as I said before. Limiting oxygen concentration considers inerting. Burning behavior, a property that not a lot of people get. And I was at a seminar about 10 years ago where one of the speakers stood up and said, I don't know why we have this test. None of the powders I've tested even burn, let alone would be considered as a fire risk. I pointed out to him that we've had products, pharmaceutical products in particular, that burnt 100 millimeter length in less than a second, creating massive flames. And we've had several of these over my time in experience of working. If you're looking at electrostatic properties, then resistivity is something you should look at. And this looks at how insulating a material is or how conducting a material is. And this could be for equipment located in zoned areas. Charge relaxation time complements the resistivity and tells you how long a material holds its charge for. The longest I've had experience of is a pharmaceutical product which was put into an earthed metal can and over 28 days lost no charge whatsoever. So this material had a resistivity of 10 to the 17. It was extremely resistive and could create lots of problem for the processes. Thermal stability is another one you need to consider if you're drying, for instance. We have attended many thermal decomposition incidents where people haven't known that their material could ignite at a certain temperature. And they may have been running for years, just 1 or 2 degrees below the temperature needed to set it off. And then something happens, like a piece in the process stops, and the material's held there for longer than normal, and before you know it, they've got a decomposition. If they'd have had the data, they would have known the risk of working with the materials. So the first one we're going to look at now is explosion prevention. Is the material flammable? Well, the Group AB classification test will tell you that. So the material is, there's the rig on in the right-hand side there. We disperse the dust up into it, and we put a constant arc ignition source across it. And this will tell us, is it combustible group A, in which case we have a problem, or is it non-combustible group B? If that's the case, you don't have to worry about it. Therefore, none of this has to be looked into. It's conducted under BSEN 80,079-20/2 from 2016, this test. We can't get rid of the flammable material because it's part of the process, but can we get rid of the oxygen? The LOC is the minimum allowable concentration of oxygen in a mixture of dispersed combustible dust with air and inert gas, in which an explosion will not occur. It's generally higher than for gases, typically 10 to 15%, and these examples for nitrogen as the inert gas, but please be aware, we have had it down to 3%. Aluminium lithium hydride, the material you make batteries out of for cars, actually ignited at 4%. Most of them, though, are fairly high, especially in the food industry, 12, 13, 14, 15% even. We've got methyl cellulose at 10, sulfur at 7, paraformaldehyde at 6, and aluminium at 5. So if you're going to use the LOC, I always say to people, please get the value of the material you're working with, and you know what leeway you've got if something goes wrong. You could go below the minimum explosive concentration. The MEC is the minimum quantity of dust dispersed in air that is required to form a flammable atmosphere. MEC is measured in the 20-liter sphere, the same piece of equipment that we use to measure explosion violence. Sometimes the MEC is referred to as the LFL, but keep to the MEC because this is specific for dusts. On the right, you'll see 2 meters away from a 25-watt light bulb you can't see, and that's 40 grams per cubic meter, but we've had materials down to 15 grams per cubic meter. So please be careful with the MEC and make sure you know it for your finest material. The next basis of safety is avoidance of ignition sources. EN 1121 gives you 13 types of ignition source. We're only interested really in 5 of these, unless you're in a very specific type of industry. So hot surfaces, flames, smoking and hot work, mechanical friction and thermite sparks, electrical apparatus, static electricity. They're the ones we tend to look at in detail. Some of the others may be around, such as exothermic reactions, etc., or stray electrical currents, and they obviously have to be taken into consideration. But the big 5 are what I told you about. They're the important ones to consider first, but don't ignore the rest. So for statics, we look at the minimum ignition energy. This is the lowest spark energy that can ignite the optimum mixture of fuel when dispersed in air. So this is the lowest energy that will ignite the optimum dust cloud. So if your dust cloud is not at optimum, it will take a higher energy to ignite it. So this is worst case. We use a purely capacitive discharge when we consider electrostatics. If we're looking at mechanics, then we look at inductive discharge, where a 1 millihenry inductor is put in before the earth. This elongates the time of the spark and mimics what goes on a mechanical spark. Any ignition source with an energy greater than the material's MIE is capable of providing ignition. You can see the standard underneath. I'm not going to read all through that. So typical values: starch 100 to 300 millijoules, glass reinforced plastic, dust 30 to 100, sugar, you can see 10 to 30 millijoules, though this works on the finer the material, the lower the MIE. And in some cases, for very, very fine sugar, it can actually drop below 10. Aluminium in fine form can be 3 to 10 millijoules. And if you take a material less than 10 micron in particle size, it can be as low as 3 millijoules. If it's 150 micron in particle size, the MIE may be 250. So you can see particle size plays a big part. Active pharmaceutical ingredients, they can be some of the worst. They can actually be 1 millijoule, the same as gases and vapors. So be very careful when you're looking at avoidance of ignition sources or considering a process. Get your minimum ignition energy so you know what you're risking. We also look at hot surfaces. The minimum ignition temperature looks at the effects of hot surfaces on a dust cloud. You can see the furnace there clearly and the flame coming out to the bottom, where the material is dropped into the furnace and the dust cloud ignites and then causes the flame. MIT is the lowest surface temperature that can ignite the optimum mixture of fuel when dispersed in air. MIT is equivalent to the auto-ignition temperature for dusts, but please be aware you may also use the LIT for this, unlike gases and vapors, which just have an AIT. And it's used to calculate the maximum permitted surface temperature of equipment. And the range of the equipment runs from about 200 up to 700 degrees. And again, we do this test in our UCAS accredited laboratory to the standard shown there. The other test we use for hot surfaces is the layer ignition temperature. LIT is the lowest surface temperature that can ignite a 5 millimeter layer of material. Now, in America, they use 10 millimeters, which gives you a lower value. Personally, I'm with the European version, which uses 5, because you shouldn't have that deep a buildup of material on your equipment. In fact, you shouldn't even have 5 millimeters of material on your equipment. So I would rather see a thinner layer than a thicker layer being tested. And it's used to calculate the maximum surface temperature of equipment. And we use it with the MIT value. So the range of this equipment is 200 to 400 degrees. And again, you can see the standards we test to. We also can test, by the way, for any of these tests to the American standards, if necessary, the ASTM, if necessary. So what are the common most ignition sources? Electrostatics. Some dusts have very low MIE values, less than 1 millijoule. Therefore, these are very high risk when you're working with them. Other materials may have MIEs higher, but they may always present a problem because you may have ignition sources of a greater energy than the MIE. Flames and hot work. Risk is high and ignition will depend on the MIT of the dust. So if the dust hits a hot surface, for instance, if someone is welding on the other side of the vessel, which has a dust cloud in it, it could create an explosion. And I've seen several examples of plants being blown up due to this type of thing happening. Hot surfaces. Risk is moderate as many values of MIT and LIT are quite high. although some materials do have much lower values, such as sulfur or sulfur salts. Therefore, hot surfaces are still a risk, and you'll need them to ensure that your electrical equipment surface temperature is lower than their lowest ignition temperature. Electrical sparks. I've seen properly selected electrical motors or equipment being fitted in areas, and then the wiring has been absolutely awful. And the wiring has open connection boxes with open access for dust to get in, inline connectors which are not IP rated, etc. So it's not just the electrical equipment, it's the wiring, etc. that has to be considered for the case of electrical sparks. Mechanical sparks, quite a high risk of ignition when you have low values of MIE. Therefore, if you're using things like blenders, ribbon blenders, etc., or high-speed types of blenders, then make sure you understand the risk from mechanical sparks. This is a bit of a graph. It may be outdated today a little bit, but it does give you an idea of the types of ignition source which cause the biggest problems. Mechanical is the highest. So as I said, mechanical sparking you need to consider carefully. Overheating of products, as I said, decomposition in dryers can create massive incidents. Open flames, again, you may need open flames for your burners on your dryers, etc., or you may not have things in place for use of open flames. Electrostatics, lots of problems with electrostatics where people don't understand them. Do an item where they change the process thinking that it's going to improve it, or in fact, they make it worse. So having a knowledge of electrostatics is always advisable. If you have problems, come to a company like us. And before you do the change, which could affect the electrostatics, then why not talk to us? We may be able to help you. Welding, again, mostly covered by permits, but it still happens. And electrical equipment, again, make sure that it's done by a reputable installer. And the other means they haven't found out what caused it. It could be any one of the ones over there or any combination of them. But what you do know is there's about 40 dust explosions a year with injury and loss of life. It results in plant repair, compensation, and your reputation being damaged. It creates business interruption and a loss of market product. And of course, you've got to tell your insurance company. They may not be too happy to insure you next year. So hot surfaces and temperature classes for electrical equipment. You must use the LIT or MIT of the worst case material used. The temperature classes your equipment exists so that it can be properly specified for the application. If you're looking at gases and vapors, you need the T class, T1, 2, 3, 4, 5, 6. For gases and for dusts, you just basically have the temperature quoted. If dust clouds likely, then you use 2/3 of the MIT, and with layers, you lose the LIT, taking away 75 degrees off of that. Always remember, normally the LIT is much lower than MIT for dusts. Flames and smoking and hot work. Well, today, hot work should be controlled by permitting. This is common in most industries and should be taken up if you're not doing it. Make staff aware of the hazards, avoid a likelihood of common ignition source problems. Smoking nowadays is banned in hazardous areas and only permitted in designated areas, and staff must understand this. Often control all access to hazardous areas. In other words, only allow certain people into these areas who have been trained to work in hazardous areas. Electrical equipment for dust. Well, electrical apparatus in hazardous areas must be suitable for use. It must be looked at the MIT and LIT for the surface temperature. You must know the classification or zone of the area. Is it a zone 1, a zone 0, a zone 2, or for dusts, is it a 20, 21, 22? What's the ingress protection rating? Make sure it's suitable for working in a dust atmosphere. And the type of powder. Is it conducting or insulating? Both of them provide problems. If it's conducting, then you have to be careful. You could get a short on your electrical equipment. If it's insulating, it could provide electrostatic sparking problems. A typical sign on your electrical equipment or the coding on them is CE, the European conformity, EX in the hexagon, which tells you it's suitable for explosions. A Group 2, Category 2 piece of equipment. Group 2 means it's above ground, and Group 2 means it's suitable for zones 21, 22. Sorry, zone 22 only. D means it's for dust. EX means it's been tested by a certified laboratory. TB is the type of protection. 3C is the type of under Group 2, Group 3 for dusts. TAT is the temperature class, and DB is the equipment protection level. So that is now within the EU. We have D for dusts, DA, DB, and DC. The electrical equipment must be installed and maintained by competent personnel. We recommend Compact certified people. Ignition by mechanical equipment. 6 potential ignition sources. Could be hot surfaces, could be flames and hot gases, could be mechanically generated sparks, could be electrical ignition sources, except stray currents, could be static electricity. If you're using equipment which may be mechanical and have the potential to create sparks, then you need to do a non-electrical equipment ignition risk assessment. In short, a NERA. And we recommend you do this and make sure your equipment is safe. Mechanical is quite a high risk of an explosion happening. So how do you prevent mechanical sparking? Reduce the energy of lower than the MIE by using, say, slower rotating equipment. Don't allow trapped metal and foreign bodies into the equipment. Make sure you have a way of removing them or preventing them getting in. Have externally mounted bearings and steels rather than internal ones. Control material feed rates. Don't have them coming in too fast. Monitor the temperature of your bearings, etc., so you know if a problem is going to occur. And make sure you have a maintenance, inspection, and lubrication system in place. Preventative maintenance. Don't wait for something to go wrong. And make sure you have good housekeeping. Clean up the dust around the area and make sure there are no layers or dust clouds outside the equipment. The photograph you see is one I took on a food manufacturing plant. They didn't know that their material was hitting, their blades were hitting the end of the dryer. And if you look there, you can see clearly the score marks going round, which could create a mechanical spark. So the typical risk assessment for a NERA. Look at the CE markings, understand the IP ratings, know the speed of the moving part. What is their rotational speed? Earthing. Is there good earthing on the plant? And have you made sure that all parts of the plant, including the rotating blades, are earthed properly? What are the materials of construction? Are they steel, aluminium, a mixture of both, phosphor bronze, brass, etc. Look at the temperature rise and the rating of the equipment for temperature. Emission of sparks, can this happen? Selection of materials to avoid electrostatic charges. So try not to use highly insulating blocks of material that could result in isolated conductors, for instance. Avoid frictional contact between steel and certain alloys. If you have rust present in any shape or form, then you can get a massive spark out of it, and this could be well over a joule. So be careful when you're using steel and certain alloys, such as aluminium. Minimize the leakage of dangerous substances from the equipment, and look at the effect of dust layer on temperature rise. Make sure you've got operating procedures in place. Again, maintenance. Make sure maintenance understands the issues with the piece of equipment and maintain it accordingly. Look at the operating environment you're working in. Has it got flammable atmospheres around it, for instance, if you're in a hazardous area? And what sort of prevention systems do you have in place to prevent an explosion happening? And how do you mitigate it? Are you following the manufacturer's instructions? In other words, do you have a correct installation of the equipment? This is just one of many types of equipment you could have around. And here's an example of where you could have problems. The gearbox on the motor could overheat. Electrostatics, creating isolated conductors. Rotating blades, providing friction, impact, or grinding sparks. Hot surfaces on the motor body and bearings. Mechanical sparking, contact between the baffles and the casing. They're just a few that you would look at when you're doing an ERA. Looking at static is one of those which are regarded as the black art. Some people think they understand it. Some people actually do understand it. But as I say to people, a little bit of knowledge is a dangerous thing. So unless you know properly about static, leave it to the experts to consider it. It's the only ignition source explicitly mentioned in the Dangerous Substances Explosive Atmospheres Regulations for the UK and ATEX within Europe. Static electricity is generated wherever movement takes place, as you can see with the pictograms on the left. Movement through pipes, pouring, walking, rollers, spraying, and dropping into silos, etc. It's often intrinsic to the intended process. In other words, when you're moving materials around, you're creating static charge. And it's a very specialized topic. You could do something to what you think is going to improve the situation, where instead you could make the process extremely dangerous. So if we're doing an electrostatic assessment, is there a flammable atmosphere? Can we get charge generation? Movement creates charge. If we get generation of charge, can it accumulate? How much energy can it accumulate? And how does this discharge? Does it discharge via a spark or like a cone discharge, for instance? So having an understanding of these properties will let you know whether you have a high-level static hazard. If we look at the different types of discharge mechanism, we have corona discharge, the sort of thing you hear when you walk past an electric pylon. It comes off a sharp point or earth conductor, or very close to a highly charged object. It's about 1 to 2 millijoules. So it's non-incentive for dusts unless it develops into a spark. Brush discharges, take your jumper off at night, a nylon jumper, you'll see those little sparks. They're 3 to 4 millijoules of energy. So charged insulators are discharged to an earth conductor. Gases and vapors can be ignited by these, but now they understand that dust cannot be ignited by brush discharges. Spark discharges are the most common. These come from isolated conductors and they go to earth. Calculated energy, half CV squared, normally between 0 and 100 millijoules. All gases and vapors can be ignited along with dusts and mists, where the energy is greater than the MIE. Cone discharges occur when you're filling, for instance, a storage silo. The powder goes in and forms a cone within it. If you have a highly charged insulating powder, then you can get up to 150 millijoules of energy from the cone discharge. This will depend on the granular size, and in this instance, the larger the granule, the higher the risk, and also the wider the silo, the greater the risk. Again, gas, vapors, dusts, and mists, where the energy is greater than the MIE. The worst one is propagating brush. And this is where normally you have a thin deposit of highly insulating material on a metal substrate. In other words, you form an electrolytic capacitor. These can have discharges up to a joule. So if you have soft insulating plastic, for instance, going around a 90-degree bend on your transfer system, it can smear on that bend and you can get a propagating brush discharge. One of the incidents I looked at was where this happened, discharging into a silo. The explosion blew the whole pipework off and blew over the actual tanker that was discharging the plastic. Gases, vapors, dusts and mists again, energy greater than an MIE. So propagating brush discharge is the one you want to try and avoid. So, summary avoidance of ignition sources. Consider the 5 we talked about most: hot surfaces, flames, hot work, electrostatic ignitions, mechanical ignitions, electrical, and those things are the most important ones, but don't ignore the rest from the 13. Perform hazardous area classification, making sure all equipment is suitable for use in that zone. Consider more detailed assessments for electrostatics, looking at electrical equipment and mechanical equipment. Control all naked flames and hot work by permit systems, and obtain suitable flammability data on your products. If you change your products or provider, get the data, please, again. Then you can understand if a potential source of ignition can become active and effective. If it becomes active, is it effective? And then you have to write a detailed basis of safety report covering everything you found. The final one we're looking at is explosion protection. This is quite often used in industry as a cheap and easy way to protect the equipment to save you losing the equipment and harm to people. In Imperial Sugar, this happened in 2008. This is sugar. You can see the state of the building. As I said, some things you don't think are dangerous, but this is what sugar did. 14 deaths, 38 injuries, explosion fueled by accumulations of sugar dust, but they allowed propagation throughout the building. Poor housekeeping, no isolation, so the explosion propagated throughout the building, with the explosions getting larger and larger as the material exploded further on down the line. These are what we call secondary explosions. So 20-litre sphere is what we test on. There's one on the right. This gives you the maximum explosion pressure. The dust constant, K is the constant, ST is Staub, for German for dust, is calculated from the maximum rate of pressure rise in the sphere and transferred over to what it would be in a 1 cubic meter vessel. You need this data if you're using venting, suppression, or containment, which you're using as your basis of safety. Conducted to there again, and the typical values we get, ST0 is no explosion, ST1, 0 to 200. Now, you looked at the sugar explosion in Georgia there. This says weak explosion. So please believe me that a weak explosion can take out your factory. This could be powdered milk, charcoal, sulfur, sugar, zinc, wood dust, any of those things. ST2s are the next highest up, 200 to 300, described as a strong explosion, cellulose, wood fire, polymethyl acrylates, etc. And the big boys, the ST3s, greater than 300, no upper limit, very strong explosion, anthraquinone, aluminium about 650, and magnesium, aluminium lithium hydride 1200, hydrogen air 550. Now you get to see what a dust explosion can do. If you're using explosion protection, you must look at mitigation of risks. Reduce the number of employees, avoid propagation of fires and explosions, unlike the sugar explosion we saw. Look at explosion relief arrangements. Take explosion suppression into consideration, or you may decide to take containment. Personal protection equipment may be required. If several dangerous substances are present, then you design your system for the worst case. And look at safe handling, storage, and transport of dangerous substances, and include the waste into this. Too many people tell me this is just waste. Here you see an explosion. In a closed vessel, the pressure will increase, and we have DPTT, the explosion rate of pressure rise, and the maximum pressure at the top. If we look at containment, isolate pieces of equipment where explosions could occur. All isolated plant must withstand the overpressure of the explosion. Good things about it: no release of combustion dust products or toxics, no requirement for provision of a safe area. On the other hand, the equipment can be very expensive to build, and it must be maintained over its lifetime. And the people who maintain it have to understand there are 27 bolts around it because it is a containment vessel, not just to stop a leak. Requires pressure testing and the documentation to go with it, and the equipment is extremely heavy. We look at containment, all parts of the plant must be made strong, including any pipes, ducts, or flanges which are included, must withstand the maximum pressure that is expected, and as I said before, must maintain the strength over its lifetime. Must be explosion pressure resistant or explosion shock resistant. And always remember, a strong plant is expensive to build and can be difficult to operate. It's not as simple as you think. The most common way we use is venting. This protects plant and personnel from the effects of an explosion. It has a controlled release of pressure via weak openings, such as the vent panels. Vent sizing is designed by KST and 20-litre sphere data. Good things: gives the ability to control release location, uses passive protection systems, can be retrofitted to weak vessels. However, combustion products and overpressure can be released, and non-flameless systems lead to explosion propagation. Advantages: can be designed in-house, cheap to vent, needs little maintenance, very wide range of application. Disadvantages: the material is released into the atmosphere, unsuitable for materials that are toxic, corrosive, must discharge outside the building, restricts the siting of the plant item to an outside wall, and you need a large safe area for the explosion vent to operate. A common thing today is happening is flameless venting. These are special devices attached to the explosion vent that can stop the flame going outside. QUR, Flame Quencher, a couple. The efficiency is reduced compared to a Burskin disc, and they need to be type tested. Flames prevented from exiting the vent, but high pressure and smoke can still fill the workspace and still can happen around the area. They require regular maintenance, and they must be suitable for materials being processed if they're toxic. Caramelization. I saw one where they were using sugar, and when they took it apart, the whole flameless vent was stuck together with caramelized sugar. So if you have a material which does that type of thing, then reconsider whether you can use flameless venting. Sometimes they use explosion relief doors. Useful, they don't require replacement, easy to maintain and cheap to fit. Problems you get is the door closing too fast after the explosion. They weather badly, and therefore they're not often as good as when they were first fitted, and often a failure for people to maintain them properly. If the vent opening closes after the explosion, then you get a vacuum formed as it cools down. VDI 3673 provides information of the sizing of vacuum breakers for this type of case, so don't let the door close too fast. Flame propagation. Most of the fuel air mixtures will be expelled from the vent and burn outside the vessel. The length of the flame can be predicted. It's about 8 to 10 times V over a third, never more than about 60 meters. For gases, about 5 times V over a third, but it's not easy to calculate the width of the flame, so we don't know how wide the flame is going to be. If there's outside dusts which are in the air, then the flame could come out and ignite those. Some of the things we see: leaking, badly maintained vents, covers on them to stop water ingress. Explosion protection suppression. This is often used on plants where you have toxic material. They extinguish the explosions in the early stages. Injection of pressurized suppression agent at a given point. Good things: no external effects of the explosion, suitable for use for toxics. Bad things: reliant on effective explosion detection, and they're very highly specialized design and installation. So advantages: no release of material, no restrictions on where the plant is located, no flame propagation, well-designed system incorporates isolation measures. Disadvantages: very high capital cost and maintenance costs. Only works when operational. After activation, you have to recharge the bottles again and get the system checked out. And obviously, when you've injected the inert into the system, you've lost the product. Couple of examples: fluid bed dryer, dust collector. Isolation necessary to prevent pressure piling effects and flame jet ignition. Without isolation, the explosion in secondary vessels could be more severe than what the design criteria are. The secondary explosion. The secondary explosion is a value of twice what the initial one starts off at. So if you have 8 bar in the first vessel, you pressurize up to 2 bar, Then you get 8 times 2, that's 16 bar of pressure in the second one. Typical isolating equipment, rotary valves, fast closing valves. The rotary valve will stop an explosion, but it won't stop fire getting around it. So, a summary for explosion protection. Determine flammability characteristics of the materials. Review the SDS, the safety data sheet, to see if the materials have other hazardous properties. Look at the hazardous area classification to identify equipment location. The venting and suppression systems need to be designed and installed correctly, as should fire protection. For containment, the vessels need to be certified for use at the pressure, and maintenance need to be trained specifically for pressure vessels. Location may be a problem for venting, needs to be placed near an outside wall, and confirm suitable isolation is in place. Assess special procedures such as hot work, management of change, and permit to works. And again, personnel working in the hazardous areas should be correctly trained. So, overview of the basis of safety, a combination of measures relied upon to ensure safety, highlights the aspects of design and operation that's safety critical, many items to consider which we've been over, equipment, procedures, deviations, human factors, material properties, level of acceptable risk. For fires and explosions, normally 3 choices: explosion prevention, avoidance of ignition sources, and explosion protection. Explosion prevention, several ways to achieve this, including change the flammable material, not often possible, remove the oxygen, inerting, make sure you have the LOC, work outside the flammable range for gases and vapors, not really possible for dust as powders are not homogeneous. Maybe you could work below the MEC if possible, but always remember that if you've got an extract system below the MEC, occasionally you'll have a shot of dust above that value. Avoidance of ignition sources. We talked about the main 5, but always consider the 13 potential ignition sources as listed in EN 1127. The most common ones, as I said before, hot surfaces, naked flames, hot work and fires, electrical, which are poorly installed and maintained equipment, and the cabling, electrostatic discharges, not a good knowledge about electrostatics or how to deal with them, mechanical sparking, unsuitable mechanical equipment being installed. Material properties for powders and dust. You need test data such as MIE to look at electrostatic and mechanical ignition. May all be also necessary to get further electrostatic data. Powder volume resistivity, charge relaxation time, or chargeability. How does it charge up if it's moved through certain materials? Is a material conductive, static dissipative, or insulating? Minimum ignition temperature considered for mechanical ignition and hot surfaces. Layer ignition temperature considered for hot surfaces. 20-liter sphere when you're looking at explosion protection. Limiting oxygen concentration for explosion prevention, and you may also need to consider the minimum explosive concentration. So, summary of the basis of safety. Hazardous area classification is your first port of call. Then look at potential ignition sources. If required, then you may need to do a specific electrostatic order, especially if MIE is seen to be low for dust or there's gases and vapors present. The same may occur for mechanical equipment, that you may need to do a specific one for that and one for electrical equipment as well. Look at the equipment specifications and the suitability of it for using with your material. Make sure your operating procedures are all correct, updated, and available. Do your risk assessments, taking into consideration everything we've talked about today. Look at material flammability, such as electrostatics, thermal instability properties. Assess the process to understand manufacturing hazards when you're charging and discharging, mixing, etc. You need to look at each stage of the process for this. Look at process and the maintenance procedures, such as hot work permits, management of change, permit to work, etc. And look how maintenance handles your equipment. They should be using preventative measures to keep the equipment safe. Make sure personnel working in hazardous areas are correctly changed, determine what basis of safety can be used, and confirm that is suitable once all information has been analysed. And thank you very much for your attendance. Very sorry about the late start, but we did have an issue and a problem with it all. But hopefully now you've stayed through to the end to see the presentation in full. I'm sorry I can't take any questions at the moment, but if you'd like to drop a message to info@sigma-hse.com, then I will look at them and get back to you in due course. Many thanks.